I would like to thank the two co-directors, Daniel Cox and David Price. They use based at the University of California, Davis. So I'd like to thank them for making this possible. Before we start, I'd like to actually introduce Professor George Langsford, who is the Dean of the College of Arts and Science here at Syracuse University. He is also himself a neuroscientist and a biologist. And so it's most fitting for him to tell you a few words on behalf of Syracuse University. Thank you, George.
Thank you very much, Christina. It is indeed a pleasure to be here, and I want to, on behalf of the faculty and staff, for all of our visitors, welcome you to our campus and to this workshop on soft active materials. It should be a much nicer day in Syracuse this year. But anyway, since you will be spending a lot of time inside, it's probably okay that it's a little bit cool outside, and it should warm up by the end of the week. But anyway, this is my first year here at Syracuse University's Dean of the College of Arts and Sciences. And one of my first official duties when I arrived in August was to welcome a group of scientists to our campus for one of the workshops that was being organized by the physics department that was on gravitational waves. And I think it is fitting at the end of the academic year that I have the opportunity to welcome visitors again for a workshop that's organized by the physics department to our campus. So it shows how active our Department of Physics is and all of the work that they do to make sure that we remain at the cutting edge by inviting wonderful individuals to our campus to give presentations. I want to especially thank Christina Marchetti and Jennifer Schwartz for the hard work that they put into organizing this workshop. I know how much work it does take, and Christina, I really appreciate the efforts that you have put into this. So join me in thanking Christina for acting. I know that there are co-sponsors who helped with this. This is truly a multidisciplinary activity, and individuals from the biology department, Laura Welch, I think, has been very active, James Henderson, and from, I think, the engineering department, Alpana Bashkaran, who has also spent some time working on this. Is he in physics? Okay. Okay. Great. So anyway, it's really wonderful that we have all of you here, and I'm also pleased that we have some distinguished guest speakers who are here from France. Jean-Francois Joanny is here. Is Jean-Francois here? Not yet. He will be coming. And Jacques Krause, is he here yet?
That I don't know. He's speaking today. So.
He's speaking today. He should be coming. Anyway, it's wonderful to have these distinguished individuals joining us for this workshop. As Christina mentioned, I'm very interested in the subject matter of the workshop because it is part of my own research. We are very interested in the cytoskeleton and molecular motors, and actually my postdoc will be presenting at the end of this conference. But I'm always very happy to bring together groups of individuals that represent a broad cross-section of the sciences, the physical, the life sciences, the quantitative and computational sciences. And I think that's really where the exciting new discoveries will take place, at the cutting edge between these different disciplines. And I know that polymer science and biomaterials will remain some of the areas where there will be significant breakthroughs in the near future. So I'm sure that this is going to be an exciting workshop. Again, on behalf of our faculty, staff, and students, I welcome all of you and wish for a very successful
entire workshop is being webcast live. That was told by our technical people here that it would be good for people to use the microphone actually. Anyway, thank you. Sorry, they told me after.
Okay. Thank you.
But thank you very much for that.
Sure.
Thanks. So the speaker should make sure to use the microphone even though the room is not that big. So without further ado, I think we can get started. First person who did the first session is Narayan Menon from the University of Massachusetts, London. So please, and I guess you should.
I'll use that. I'll give that.
Oh, yeah, okay. That's your clients. Yeah, I wasn't calling on a client. But thank you. I'll leave it to you.
So, welcome to what promises to be a nice session. Okay, so we're going to start. So we have 4 talks in the session with a break in the middle. We start, so the invited talks are 35 minutes and I'll give the speakers a 5-minute warning. And the contributed talks are 15 minutes and I'll give you a 3-minute warning. We start today's session with Arshad Kudroni from Clark University, who will tell us about swarming and swirling, from granular rods to bacterial colonies. Arshad, you should use this one. Right.
Jason will tell you what you need to do.
Okay. Not perfect, you could say.
Should be. Is it on?
Is it on? Hello?
No.
Yes. Hello? Here, back.
Christina, Arpana, and Jennifer, who have been really helpful in getting us all here. And it's wonderful to be here. And the weather not being so optimally great for us, right? I mean, it's the beginning of spring, and we don't want to be stuck inside. So this is you can look at it as a glass full. All right. So today I'm going to talk about an experimental approach, and what we're going to start off with what is called granular materials. Okay. This work, I should acknowledge my contributors, because what I'm going to talk about has been, has come about because of interaction with so many people, so it's very hard to distinguish what are my ideas and what are other people's ideas. Let me just acknowledge, and if there's a pointer. Then Kevin Safford is a graduate student at Clark, and Jeff Lemay was a visiting graduate student, who have done this work here, which you're looking at, which are essentially what I call self-propelled particles, which are basically passive little rods. All right, so something like this. It could be your fork. It could be anything which is non-symmetric, and if you put it on a vibrating table, all right, then they can form self-assembled structures. So here is one simple example where they all go and form a ring. They assemble at the outside, even though there's no chemoattractant or there's no gravitational potential driving them there. All right. So just by doctoring these passive particles and giving them some activity by vibration, for example, you can make them do things. All right. So if you like, the goal here is to try ways and means of finding these particles to do different things. So these are the experimental students, and then my collaborators, Dimitri Wilson and Lev Svierings. Lev will be actually here. I think he's not already here. And he'll be speaking about something different, but here he has contributed a lot in our understanding of how, if you like, a pen, if you like, bounces on a table. All right. So that is one approach to this problem, and so they have contributed a lot, and you will see that throughout the talk. And Mehran Kardar and Cantor have helped us sort of make connections with polymers, right? So polymer physics and how can that be applied to granular materials. Right? Okay. So going on. So the way we got into this, or towards this active matter material, was sort of by accident and sort of almost a decade old. And we were growing Bacillus subtilis colony, which are basically 9 micron long bacteria, which are swimming around in a broth. All right, and then we looked at it, and if it was at a certain concentration, they would swim around merrily. They would form, sort of what are called Fisher wave patterns. And if you sort of allowed them to grow for a long time, they got dense, and then they look something like this. All right, so where you can see locally they may be ordered, and there may be local activity going on. And what has changed here is just the density of the particles or the density of these bacteria. And then we wondered what was going on here. Was there more nutrients here? Was there, was there a little bit more density over here for them to move around? So these are all essentially bacteria which are swimming in a thin layer because they like oxygen, and so they have to be near the surface of the broth. And we asked what would happen in this case. All right. And, this is a very complicated problem. We can't tackle that as with the expertise that I have in my lab. And then, you would work at it from a theoretical angle, and then you see that people have talked about it for a long time. And, starting with the observations of tobacco mosaic viruses more than 100 years ago, which show that these are locally ordered over here. On Sagler and collaborators and many others have worked on this and shown that, basically it's the best or efficient way of packing material leads to this ordering here, or entropy maximization leads to local ordering. And in the liquid crystal community, you have seen a lot of these sort of isotropic states where essentially rods align in a certain direction. They can form symmetric patterns where they are not only aligned, but also have density variations. Right? So they are ordered. And the question is now, in sort of granular systems, would such things behave? If you have oblate particles going beyond spherical particles, would they behave in the same way? Right? And, if you go out there, and this is a picture I took in California a few years ago now, where if you see sort of these elephant colonies, all right, so they are next to the ocean, and if you see them aggregate over there, so they seem to aggregate because they like to, so these are the females, and they want to be away from the males, and they, so they aggregate, and maybe perhaps for warmth and so on, but what you can see is that, successive seal will come in and find and squish itself into place, and they essentially look like they are ordered. All right. So these are athermal particles, and again there seems to be something like local ordering. So maybe there is something like that in granular materials. So that is the sort of starting point, if you like, of what I'm going to discuss next. All right. So what we are going to look at is coming back to sort of the basics. Start off with particles which can only interact when they're in contact. All right. So these are particles like this pen or this here. So they only contact when they interact because there's hardcore repulsion between them here. All right, and there may be some friction. All right, so that's why you have to sort of drive them in some way to sustain motion. All right, so that is the essential thing. And so what can you do with this? All right. So as soon as you go away from spherical particles, you have a lot of choice as to how to go about beyond spherical particles. So we have sort of started off with rods. All right. So. And first time we sent a paper in TRL, we thought, rods? That's too particular. Anyway. All right, so you start off with particles like this, and then you have a choice, even in that. All right, so now you can have this rod which has a certain flexibility. All right, so it's a floppy thing, right? Or it's rigid. Or you can have something which is slightly apolar. So that is to say, polar. That is to say, one end is slightly different than the other. Right, even within a rod. And so those are the two choices that we can come up with already. Okay, and we can ask if you have such particles, all right, in a table, all right, and then we are just giving them excitations. How would they behave? All right. So then on top of that, you can build extra things, which is you can have a fluid now. There could be interactions between the fluid, through the fluid, and or they could be potential interactions and so on. And then we can perhaps one day actually describe the motivation slide that I gave you. Right? But this itself is very interesting from a granular point of view itself. How does earth thermal particles behave in such a way? All right. So what we can do is essentially open up a book of Dewey and Edwards, all right, and then start from that and just try and sort of see how much of that can we actually see in our system. Okay? So that's the point of view that I'm going to take. And then what are the extra things going beyond sort of thermal physics? So what can we see in terms of convection? Are there currents in such systems, vortices? So can you see ratchet motion and so on? So those are the questions that we have in mind as we go forward. All right. So to organize the rest of the half an hour that I have here, what I'm going to talk about is essentially a phase diagram, if you like, where if you're changing the anisotropy, here I mean that it could be apolar or symmetric particles, all right, which of different lengths as you go along this axis, all right, or you can make this asymmetric, and so you could have one head and a tail over here, and then you can change that degree of anisotropy as well. So this is that axis, and over here you can start off with one particle and ask how does it move on a vibrating table, all right? What are its properties? What is so particular about vibration versus just being excited by thermal noise or by it just propelling by its flagella, for example, all right? And then we can ask as a function of volume fraction, density, concentration, what happens in this case as these particles start feeling each other, and because of excluded volume effects, what kind of effects will you do? All right, so that is essentially sort of the organization of what I'm going to talk about. So I'm going to start from here and then go to the right. Okay. So the system that we have in mind is essentially so pens and things like that, or the chain that we have in mind here, which is our flexible rod, is essentially a beaded chain. All right, and it may have a head or a clasp at the end, or it may not. All right, so that's what the system that we have in mind. All right. So here is our experiment. Okay, just to give you some phenomena as to what happens, and I think it's not right to just go into too much detail in the first talk. So here is our system. All right. So we have a vibrating table which was built by Dan Blair. All right. So this is essentially a saucer, if you like, which is vibrating up and down. And why do we need to do that? Because if you just leave a particle here, it will stay there. All right. Because of inelastic collisions, it won't move. And therefore, you have to continuously excite the system to keep it moving, right, to have a non-steady equilibrium state. And so you have a particle like this, and then on top of it, we put a chain, all right, so linked chain of different lengths. So this one over here, which just played. Here is one which has over 1,000 particles, just over 1,000 particles, all right? And so on this plate, you have to excite and you have to sort of parameterize what's going on. So gamma, you will see all throughout this talk, is basically the strength of the vibration relative to the gravitational strength. All right? And so there will be a frequency of vibration. You can treat the surface differently. You can have a rough surface, smooth surface, and then ask what would happen in this situation. All right? So how does this chain behave? Does it look like essentially it's pulsating or moving like what you would imagine a polymer would if you could visualize it? Then, can it be described by these self-avoiding walks and so on, because, there's excluded volume effects between these particles. That is to say, if you start off at one end here, you go along, all right, take random steps so that you're avoiding each other, all right, each particle. And then in this case, for example, the radius of gyration will not, as in a simple random walk, go as, n to the half, n is the number of steps that you take or the number of particles that you have in the system. And in this case, because of excluded volume effects, you should go as 3 halves. Right? So it should be a little bit bigger because they're trying to avoid each other, so they'll spread out a little bit more. And so would that kind of effects be seen? All right. And then because we have chains which are, again, bend only so much, right? So this is one bead, so this is one particle, this is the next particle, and the third particle here, but the maximum angle that it can have is 45 degrees. All right? So if you play with one of these chains, it can have a maximum of 45, or minus 45 in this case, and they can be in any of those configurations. Right? So it's a flat distribution. And so in this case, what we can do is just use the persistence length of the random walk, right, as a parameter to describe the persistence length, and that turns out to be about 10 B diameters. All right? So you take 10 steps before the bond here is uncorrelated with the bond here. Okay? All right. So that comes into play, all right, shortly. All right, so then if you vibrate a whole set of these sort of beads, beaded chains, so you can start off with 4 beads, all right, 8, and so on, and go up to a large number, so there's, let's say, 1,000 here, which is almost seeing it is seeing the edges, and in this case, the boundary effects start becoming important. And if you plot that, all right, then as I showed you, the scaling should be 3/4 if it was a self-avoided random walk in an infinite system. But because we are in a finite system, this is the radius of gyration of the container itself. So as soon as you start approaching that, the radius of gyration of the plate starts to, of the chain starts to approach that. Okay, so it's sort of bounded by that. All right. Down here, well, the data seems to be described more by an exponent here of 3/4, but is that a fluke compared to 1? We don't know. All right. So this is sort of the first structural parameterization. You just ask how big is the chain, right, on a plate, and this is what it is. All right. So then we need to look at it a little more carefully to understand what's going on. And so for that, we need to look at the pair correlation function. So that essentially describes if you have a particle here, all right, then, you know, at some distance or some wavelength, what is the probability? Okay. So then, and then Fourier transform that. So then you start off with as a function of wave number, all right. This should start off with at 1. Okay, so this is what is being plotted, and it should decay. And this, if it was an infinite system, would be or chain with walking around an infinite system, it would scale as 4/3, excuse me. All right, so that is that line, and that's not the case here because again we are not in an infinite system; we are in a finite system. All right. So to make a comparison with sort of the zeroth assumption that this is a chain essentially moving around like a avoided random walk, you have to do a simulation, and that's what Jakob did. All right, and I'll describe in a second. And in that case, all right, Jakob does simulations in which he produces a random walk with the same persistence length, and that is to say every angle is the same here at 45 degrees or minus 45 degrees, uniformly distributed to the same number of chains, does it multiple times, and generates a curve. All right, and that is the line that you see going through the points. Okay, so here, in some sense, Jakob said, well, you got to do the first thing first. Okay, so first, ignore the fact these are avoiding. Right, just start off with a Gaussian chain in which things are just going through each other, and indeed, you can start off describing the properties of a length 4 chain, 8, and so on. Excuse me, 16, 64, and so on. Only when you get up to the higher numbers here, 256, that you actually start seeing deviations from the simplest model. All right? That is to say that initially the chain it doesn't intersect itself often enough for it to be really possible for you to tell that it is actually self-avoiding. It doesn't matter. It's really dominated by persistence length. Okay. So if I had just stopped here, you know, I was just fooling myself or fooling ourselves. Okay, that was good or bad. Right? So it's only when you get to longer chains that self-avoidance comes into play. And in this case, all right, when you plot the structure factor here, all right, for the data here, you can see that it's clearly defined better by the self-avoided random walk rather than the random walk itself. The random walk will always be on the top side because things will be more squishy or squished together if it was not avoided, and so the signature of that would be higher. All right, and so as you get longer, you can see that is preserved. Right? So in this case, you can see that at least, all right, that the structure of this chain, which is now, you know, frictional, is being excited from the outside. None of this, you know, we would say ahead that it should be described by a simple random walk, is described by a simple random walk. Actually, sorry, this here. It's not an it's the simulationist who is doing. So what he does, it's an artifact of not enough averaging. Okay, so you have to produce random walks inside a container, and so you have to throw out, you know, as the chain length becomes larger and larger, more and more because they go out of the container and so on. So he starts to lose it, especially it's 1,000 and you can keep 1, and then he averages, and so experiment in the sense that you can do jet statistics more efficiently in this case at least. All right? So that's why this is oscillation, but it's an artifact. And it decreases as we increase the number of averages. Okay. Right? So this is the description, if you like, of the average extent or sort of length scales in this polymer granular bead. And then we can sort of turn now to dynamics. So dynamics, so here you can ask how fast does the chain move, and so is it diffusing and so on. So here starting with n is equal to 1, one bead will diffuse so much, and then as we increase the length of the chain, it will start to decrease. Right? So heavier particles will, or more mass particles should diffuse less, and so that's what that trend is. And so we can extract the diffusion constant from this. Okay, from the linear part. It's not an exciting scale over here. It's all barely over 2 orders of magnitude, but granted that's what it is. All right. So then, if you extract the diffusion constant by fitting those slopes of mean square fluctuations as a function of the number of particles, all right, then that should decrease. That's what we know. But now, if you believe the Roos model, all right, the Roos model is where the simplest model, where you have each monopore experiencing a viscous drag. So every time a bead collides with a plate, it is not only getting kicked by some and given some energy, but it's also losing some energy because of collision. All right, and each of these collisions are independent. So one bead is colliding here, and then the other, and they are indistinguished. So it actually is a better approximation here than actually in the fluid. Okay, and so in this case, you would expect the diffusion constant to go as 1 over n, all right, with some free factor, which is the thermal energy scale here, and c, which is the drag of the polymer in a fluid. Okay? So once we do that, we can extract that. You can see that this falls in a straight line except for particle number 1, which is sort of a little bit different anyway. All right, then we can go back, scale this back, all right, with the time. And then we can see, right, that all the radius, the mean square deviations scale on this new time scale, right? Scale time scale. So here this is the collapse, and this is actually a better way, I think, of showing that over now 6 orders of magnitude that it is actually diffusing linearly. All right. So you change the length of the chain over from 4 to all the way up to 1,000 or so. You actually collapse it with the same drag coefficient. Right, so this actually is a test of how our beaded chain is interacting with the plate. Right, so it is essentially behaving like a thermal fluid, if you like, which is giving and taking away energy, and this is the drag. Right, so now we can sort of use this to build a more elaborate. Right? So I'm going to skip ahead of this. Now, if you can ask, what is the diffusion of more than one? All right. So if you put here, so we have taken chains of different kinds. So we're using a tracer technique in the sense that we have the black beads over here, which are 8 in length, and there are many of them. You may or may not be able to see them. And then there are silver-colored beads here, which you can actually see. All right, and then this is 8, so this is just barely below it's of the order of the persistence. Right, so we start off with sort of essentially slightly flexible polymer here, and then we are vibrating that in a small density over here. And then as one increases the density, what you can notice is that while this is sort of flopping around a lot more, this is less so. All right. Plus, it is diffusing less. All right. So this is what I'm going to say here in number 1. Okay. So if you look at the root mean square fluctuation in this case, yes, as the area fraction increases, because of interactions with the neighbor, the root mean square fluctuations decrease. All right. Here, this is calculating if you have a certain orientation of the polymer, all right, or this flexible rod, which is essentially gotten by fitting the shape of the polymer here. And then if you ask if it turns through an angle here, what is the angular orientation? How does it change as a function of time? And indeed, that also decreases. All right. So things are now getting sort of stuck. So another way of seeing, and when that happens, is that it should go as the aspect ratio should go as 1 over the volume fraction or the area fraction. That is to say that it's not free to move anymore. There are other particles nearby, which makes it stuck, and that's roughly where it happens. If you look now if you look at the fluctuation of the polymer along the direction of motion or perpendicular to the direction of motion, then also what you can see is that the parallel component here is decreasing, all right? But the perpendicular component, which is the same order as the parallel, so this is plotted on the same scale, so you can see this and this is roughly the same slopes and the same. Then the perpendicular component decreases more than the parallel component. So this rod is getting more and more confined in the system as it goes on. Okay. What we're trying to do next is sort of scale this appropriately, but again, we'll do that. All right. So we'll go on with the story. Okay. So now this is, if you like, we started with the story with the flexible rods. Now we can go on to rigid rods. Right? So just like a pen here, and you can start off with a rod, but you can also start off with a dimer, which is basically two balls here connected with a stick. All right, that makes it to visualize easily. And what you might expect here is some more like this. So you just drop this. All right, so it might rattle around, and that's what you observe. And you might not expect overall drift in this case, but as you may have seen here, if you excite it ever so slightly, gently, all right, so that the acceleration is less than 1, and you just drop this piece of particle on top of it, it actually moves directly. Right? So because of spontaneous symmetry breaking, here these particles are actually moving to the right, even though there's no asymmetry in the particle itself. Right? It's on a vibrating plate that can do that. And people have, King's group has actually examined this stochastic dynamics of a simple rod on a plate very, very carefully. All right? And so even when you have a rigid particle as opposed to a non-rigid particle, like what we showed you ahead, in the earlier part, actually the dynamics, even on a vibrating surface, is very tricky. All right. So now if you do start looking at collective dynamics, so this is actually historically the older work here. So if you put sort of many of these rods, all right, in the annulus, what one can show is that they actually undergo directed motion, all right, given depending on the tilt, and you can actually work out what's the speed with which it should go. So that is to say, the speed with which it actually moved here as a function of the tilt angle here from the vertical. So it first starts to increase from 0 and then starts to decrease. All right, so there's a sweet angle at which it actually propagates the fastest. One can sort of assign a very hard mechanics problem as a graduate problem where you try to work out if you drop a pen on a plate, all right, then what will be the forward momentum it will get from the collision. Okay? And that happens because when you have the pen interacting with the surface, all right, there's a friction force which acts on the pen, which is going to be in the direction of the tilt. All right, so that's going to couple, and you can work out the formulas, and actually Lev Smearing is the one who did the calculations, and you can actually describe these shapes. Right? That's a different story. Okay, and then if you take even more of these particles, put them all together. Right? So these are just passive rod-like particles here. Seth is the one who inspired this here. So if you take 5 sort of half centimeter long particles, something this long, they look like pencil leads. All right, you can put about 8,000 of these here initially. So we are looking down on a container containing a whole lot of these things. Then, as a function of time, all right, because the edges are more shiny, all right, you can see that local order is forming because as the shapes, even though particles may be lying flat down, they're actually pointing straight up. Okay, all right. So they organize, and then they move. All right. So here is sort of a very nonlinear or out of equilibrium phenomena where there is a spontaneous vortex formation here, or long-range convective motion appearing out on the wedge, right, or a disordered scale. Okay. And if you look at where these things are observed, so if you do a phase diagram of if you put n number of particles on a container, all right, so if you put too few, then they're going to lie flat down, and then you might see some kind of pneumatic state like this, where locally things are aligned in a certain direction, or maybe even tiles. It depends on how carefully you look. And in fact, Galanus, Losart, and Weiss have done a very careful, and also Weiss have done very careful analysis of this pneumatic transition, and that can be found here. All right, but then as one increases the number of particles, then these rods spontaneously start to stand up, and when they stand up, they lean, and when you have a leaning condition, things will move, and in this situation, we have vortex formation. Right? So we have not seen convective motion in this situation, but Narayan and Vijay Narayan and Narayan and Menon, Narayan is different, but have seen that in that situation. I'm sure we'll hear about that more in a later time. Okay. But our tack was a little bit different. There's a lot to be explored in that direction. So we said, well, let's go back and actually try to make our particles go in a certain direction, right? So I like to call this a robo-bug because it's sort of, at that time I was listening to robo-flies and robo-eels and so on. So, all right, so if you just take a steel particle and a glass particle. So here I'm just taking two different kinds of particles, just gluing them together and put it on a vibrating plate. All right? Unlike the previous case where we had to do a very subtle excitation, here you can shake it, tap it, whatever you do it, and then you'll find that it migrates. All right? This is not tilted, it's migrating to one side. And on the same table, this is in a groove. All right? So here in aluminum and steel beads, so somewhat the particles are different weight, different friction. Again, this will move to one side. All right? So here, Sano, for example, has demonstrated this before with a sort of board-like particle. So that's what I was saying. Like if you take any particle, forks, spoons, whatever, you put it on a vibrating plate, it will spontaneously move in a certain direction. Okay? So if you do that, but you want it to be a little bit more, sort of not increase the complexity so much, so we want to just break the symmetry of the particle, but not the shape symmetry of the particle. All right? So if you have a bacteria, yeah. All right. Right. So then you have one end which is heavier. Then if you put it on a vibrating plate, then it will move. Okay? So we can control the direction in which it moves. So if you put a whole lot of these particles on the plate, then that's what you saw at the beginning. So here you saw that particles essentially accumulated the edge over a few seconds. All right, this is slightly speeded up, by the way. Okay. And so here all the particles aggregated, and the way I like to imagine this is, if you are driving along in a highway, all right, if you are one person driving along the highway, there's a roadblock, you can turn around and come back. All right, if you have a whole bunch of other cars in which you're going along, each one tries to do a turn, there's going to be some frustration. Right? Things do get accumulated at the edge, and that's essentially what is going on here. All right? So if you can increase the noise, then we can melt away from here. And just so that this may or may not have anything to do with reality, but if you actually look at the bacterial colonies I showed you earlier, you look at the edges, you can see that rods, these bacteria can also align at the edges in the same direction. So there is perhaps something like this. Right? So now, if you actually increase the vibrations, you can use flips in the rods, and in this case, you can actually make the system more homogeneous. And you can describe this more thoroughly. And in this case, you can look at case here. So in this case here, we have sort of weak swirls. Right? So if you track the particles over many time units, you have weak swirls, but not on the wood seed that we saw earlier. Okay. We can. So what we wanted to do was not do this the same way. That is to say, you have these particles either stuck at the boundaries, or you form these sort of weak structures which are swirling around. So we thought, well, if you could make these chains longer and make them asymmetric, so resembling now our aspect ratio 10 or aspect ratio 5 beads, what we can do is perhaps make these swirl around more, and so this has to do that. So here we have a head. Okay, and then we have a tail. The tail is floppy, all right. And then if you put it on a vibrating plate, all right, based on all what we learned, this should move. And indeed, because of this particle here, all right, and the collision sustains, it actually moves. And this particular tail here is just passively being dragged around, right? But not quite. The tail now, because it wiggles, can change its direction. All right. So the particle can change direction because of the wiggling of the tail, and so if I take one such particle, All right, so this is we have coded it so that the particle here is the head is black and the tail is white here. You can see that it undergoes directional motion on a vibrating plate, right? So this is over about 2.5 seconds or so, and this one over a long time you can see over 2,000 seconds. It will go around on all the plate, but there is a persistence length. Right? So many body lengths, it goes in a certain direction before it turns. You can show, I have like 2 minutes maybe or something, yeah. So you can show that if you track different parts of the particle, you can show that the head vibrates less than the tail, and then you can get a sense of the direction, how long it takes before it decorrelates. All right. So here you can see that it takes about 10 seconds, or essentially in terms of length scale, about 5 body lengths before it can turn. And one can show that the speeds can be manipulated by using different lengths. All right. So why am I showing you all this? All right. So here you can sort of then look at the particle on a surface, and you can change the smoothness of the surface. So if it's smooth, because we have a directed random walk, all right, over a certain time scale, over almost 2 orders of magnitude, this scales as 3 halves, but that's nothing special. All right, it just has to do with the persistence length I'll show you. All right, so if it's a rough substrate where you can change direction more rapidly, it scales as 1. All right, but even the non-1 or the one with the persistence random walk can be explained by including sort of statistics of if a particle is moving in a certain direction, if it turns through an angle theta, then there will be a persistence interval as it turns, and using that idea you can sort of explain the diffusion even of non-1 diffusion. Right? So let me just close with this. So supposing you have now n number of these, all right, so if you have a small area fraction covered with these particles, so they just run around merrily, okay? And so they can diffuse around the system. Now, if you increase the area fraction, so it's filled, you can see that now each of these particles are sort of sometimes hopping, right? So if you look at it, it's clearly not moving as much, but some of them are hopping. And then if you increase the area fraction even further, you can see that they are essentially clustered, right? It's essentially jammed, so they are just stuck in place, right? So here they are trapped, here they are diffused. This area fraction I won't put any money on. It sort of depends on how long you wait and how you actually put these particles together. And so in this case, you can see the mean square deviation. Is there anything special here? Turns out it's almost essentially going towards linear as a function of the volume fraction. So given enough time, yes, they are moving in a certain direction. When the cage break, they can change directions, and then it starts to approach 1. Right? At least that's the initial indication. We need to do more to at least have 1 more order of magnitude here, and then perhaps we can see if this is really diffusing linearly or not. So wish I had that story for you, but I can't close with that. All right, so I'll stop here, and essentially I want to just give you a flavor of the various kinds of sort of manipulations you can do with just taking a particle which is non-spherical. All right, and then we can play this game of looking at, if you like, more thermal-like behavior in the systems where particles are essentially colliding with each other, and then try and see how much of polymers or pneumatic crystals or what can be applied here, and then go towards tune this parameter of anisotropy and ask what would happen if this is sort of a bacteria swimming around, but only interacting with collisions. Right? So I'll stop here, and if you have any questions, I'll be happy to take. Thank you.
We have some time for questions.
So I was okay, yeah.
Yes.
So with the polymer story, are there things that are different between the granular polymers and the
And the non
and the regular polymers? I mean, in sort of a follow-up is does the effective temperature in the granular system really have a direct correlation to the temperature in the thermal system?
Yeah, yes and no. So it depends on how carefully you want to ask these questions, and so on. So I won't try and go back there. But if you look at the diffusion constant calculated for a polymer, right? So it depends on the energy scale there, KT, and then C, and then diffusion number of particles. So KT you map to a granular temperature. Okay, so you calculate the fluctuations of the particle. So here it actually helps that we have these beaded chains, and that's actually one of the reasons why we're going with beaded chain. So if you look at a beaded chain and ask the temperature of that, this is the granular temperature, the scale at which it actually moves around. I didn't show that, but you can show that temperature is constant as a function of the length of the chain. So if you take a 4 chain, a 10 chain, a 100 chain, each of them, if you like, is it's a linked ball, but each of them is getting collisions from the bottom independently, and so they vibrate the same way whether they are at 4 length or 1,000 length. Okay, and so that helps, so that we can actually maintain the temperature constant. And the reason why that one particle deviated slightly is because the one particle is slightly different, it will bounce around and have a different temperature. And so if you now ask what happens if you have a rod-like particle bouncing on a plate, unfortunately the temperature in this direction is going to be different than in this direction because of the substrate and center of mass not lining up. Okay, and so as soon as you have multiple particles in the system, size particle in the system, then the temperature is going to be different. Okay, so if you keep the system in a certain way, all right, same size particle, and you change the system size in a certain way, then yes, more or less it seems to, as I showed, translates quite well. But you can go away from that, and if you have as soon as 2 different kinds of particles, they all have 2 different temperatures, as you know, in our example was shown, they're just spheres that can have. So then you have to start dealing with 2 temperatures in the system, and I'm sure it can be done too, but it's not one-to-one. It's not like taking molecules of different sizes. So there itself there is a difference when you go from that. And then you can move into more other.
So is the granular temperature dependent on the intensity of vibration and friction coefficient, or does that depend on friction coefficient?
Yeah. So yes. So it depends. So it is to over a certain range of vibrations. Okay, so it's essentially interacting with oscillating plate. So if you ask what's the velocity scale of the vibrating plate, find out that and calculate the fluctuation temperature. Those are going to go linearly with each other. All right, and the linearity is going to depend on how rough the surface is, and that coefficient is going to be larger or smaller depending on that. All right, and that's going to have an impact on C. So C is actually measured in our case, and what was nice actually, which we didn't anticipate, was essentially constant over the total. Yes.
So with the robobugs being vibrated and moving to the edge,
yes,
it was hard to see what the boundary layer was doing. Are they lining up perpendicular? Or
so they're going like this, all right, and they're just bumping against it. All right, okay. And so if there were no neighbors, so if it was a low density, all right, then eventually it would hit like this, bounce off, and come back to the surface. Okay, so but if you have many more other particles around, and if you're long, then imagine you want to.
Problem with the resolution.
So this is exactly. So this is where it is. Okay, so this is it's going here, it's hitting here, and if it's by itself, eventually it turns and comes back. You can show that. But now if you have a whole other particles over here, like this, then it gets trapped because there's not enough. You have to wait for a density fluctuation to open up for this to actually turn around.
So in a bacterial colony, what sets that boundary?
So in a bacterial colony, bacteria is more complicated. First of all, they can reverse the angles. So right, so they tumble and so on. So they're going this way, and you can actually see that video. And we're comparing pictures, so it's not fair. In some sense, there could be more going on. But in the bacterial colony, you can see that it gets stuck, okay, for some time, and eventually it just comes back. All right, or it rises towards each other and it comes back. And plus, if you look at the bacterial colony layer, so this is the this is the subsurface. If you look at it from a sideways cross section, this is the substrate. This is the agar substrate. It creates a lubrication layer like this, in which the bacteria actually swim. All right, so they are swimming here, and so over here it is one-dimensional, or quasi-two-dimensional. Over here they can actually pass over each other, so it makes it more complicated. All right, so but you can see that at least over here for a long time you can see that they are trapped going outwards. Now it's possible that it is trying to secrete more, material to create a larger lubrication layer. So in that sense, it's just inspiration. I don't think we explain anything. It could be possible, and you can go far with a physical model, but unless you go in there and you actually dwell in, I think you have to be cautionary about carrying too much of this passive to the actual diamond.
Question for curiosity. I mean, if you would take now
That's fine.
teeth instead of rods, I mean, you would see the crystallization transition, right?
Yes, yes, and so there's a whole lot of granular physics here which I swept under. I mean, in a sense, not swept. I mean, in a sense, there's a whole lot of a big community which looks at crystalline transitions, at the spheres, and the one who has done a marvelous job is Pedro Rice and Mark Shattuck, who have looked at crystalline transitions in two-dimensional, essentially similar system with beads, and they see remarkable similarities. So, if you like, 10 years ago, the granular community was going, wow, it's so different. But now, we are also looking at all the similarities with each other. And so you can use that as a building block. So you can use one side to say, well, there's a whole lot of exciting things to be discussed. On the other hand, there is a path. There is a path that you can use to understand this. It's not just a disparate bunch of operations. Okay? So I think that's a very broad answer. Right? But yes, there is something.
Yeah.
Yes.
Hi. In this spontaneous symmetry breaking you get with the
simple dimer,
yeah,
yes.
The one where you have to vibrate at low amplitude or
yes.
low frequency. Do you understand the actual nature of that symmetry breaking? I mean, can you identify and
right? So yeah.
Is it stable?
Yeah. So supposing you do this. So what I mean by subtle or so on is that supposing you have a vibrating oscillating plate. Okay. And so there are two relevant oscillations. One is below acceleration due to gravity. That is to say, if you put a particle on the top, it will just stay there, or above, and it will start to vibrate and go on higher. Okay. So that's what I mean by subtle. So if you're right around 1 or so we are just giving enough energy for it to sort of bounce back up because of loss of energy. So say somewhere we are there, then if you drop it, say 10 times, so a dimer of this kind on this plate, then 50% of the time we'll go into a mode where one end is on the plate and the other end is hopping. Okay. The other 30% of the time it could do this. All right. All right. Under just dropping different times, or you can have this mode. Okay. And now it's only when you have this asymmetric bounce oscillations that we can see that it moves in a certain direction. Okay? So then you have to consider now the various kinds of collisions which are occurring on the surface. So even just for the plate, which I showed you the simple formula for, it depends if it was dropping in this angle, whether it moves forward. You can do this on your card and you can see that it moves forward. Okay? Or if you drop it at a shallower angle, it's just going to stop. So it's angle dependent. Okay? And so for this dimer, you have actually double collision happening. That is to say, you have one contact here, and during that contact, you have the second contact. So now you see that this is, so now you have different hierarchy of collisions. So you have a rolling contact here with a collision, all right? Or you have a sliding contact here with a collision. And so there are 12 scenarios at the minimum that you have to consider, and I've considered that. And if you look at the supplement which goes along with the PRL, you'll find some of that worked out, where you can't give a very close formula, but each scenario can be worked out, and you can show that depending on the aspect ratio, it will go forward or backward. I don't know. Does that?
It's going to depend on what you average over. Fine.
Average over. It depends on the aspect ratio. Yeah, it's right.
We get a chance to discuss it in the session.
And I'm here, so we can always.
So, just in the interest of staying on schedule, we should probably move on and thank Arshad. The next talk will be given by Seth Frazen from Brandeis University. Active emulsions.
So this is a new area of research for me, and most of what I'm going to present here is very exploratory. And what we're trying to do here is These are 100 micron diameter drops. Each one of them contains a solution of chemicals which oscillate in time. And these emulsion drops are stabilized by a surfactant so they don't coarsen. Well, you do, to show this is an experiment and not a simulation. And they communicate chemically because some of the species involved in the oscillations go from one drop to another. And we just kind of, in some sense, stumbled on this system and we're just exploring its properties. And one of the things that makes it challenging is that the chemistry is really important and rather complex, and the physics has similar attributes. And so this is, by nature, a very interdisciplinary venture, and since I'm very ignorant of chemistry, it's been quite challenging. And so it's a collaboration. Most of the work I'll be showing here is due to this postdoc, Hector Ochoa, who's joint between Epstein and me in chemistry and physics. And we're also working with another professor at Brandeis who's just joined our department this year doing materials chemistry, and a number of other postdocs and research scientists from chemistry. So the chemicals that we're studying is this known as this Belousov-Zhabotinsky oscillating chemical reaction. And that's the kind of paradigm of chemical systems that oscillate. And if you just take a beaker and you pour this cocktail of stuff in there, 1 molar sulfuric acid and ceric acid and malonic, acid and ferroine and all kinds of stuff. You throw it in this pot and you just stir, it will oscillate back and forth between this oxidized state and reduced state of ferroine and ferroin. So an Fe3 plus and an Fe2 plus. And it's this oxy-reduction reaction, and will oscillate back and forth in time. And if you put it in a continuously stirred reactor where you're pouring in fresh reagents and you're just at the bottom removing the product, it will oscillate forever. And here is showing the color change, red-blue, and this is following the concentration of one of the intermediate species of bromine as a function of time. And at the basis of it, chemists will write out the detailed mechanism. Bromine plus bromate goes to malonic acid, and there's 90 steps. Something like that. Maybe some more, maybe some less. But if you're a physicist, you reduce it down to 2 essential species. So you have an autocatalytic oxidation of the bromate, which is running away exponentially, and then you have a reaction that inhibits this excitatory response, and that's due to the bromine. And then there's a third chemical reaction that replenishes the bromine once it's been exhausted, and then the cycle begins again. So you can reduce it down to kind of a two species, and if you really simplify and just take the rate-limiting steps. The chemists find this abhorrent, but it's a simple way to think about it. So, you may think that this violates the second law of thermodynamics to have oscillating reactions. We're used to thinking of chemistry as mixing together 2 reactants, and then you have simple exponential response to the product. And if you did have the free energy in a closed system vary like this, with this damped periodic motion, that would violate the second law of thermodynamics. Second law of thermodynamics says that in a closed system, the free energy just has to monotonically decrease. It can't have wiggles and bumps like that. So that is a violation. However, you don't have to just drop down exponentially. You can have some kind of interesting trajectory as your system eventually grinds to a halt. If you took that BZ beaker, the beaker I showed previously, and you're stirring it without adding in anything, it will oscillate maybe 100 times, the typical period is about 3 minutes, so it'll go for 5 hours oscillating back and forth, but eventually it will run out of juice and the reaction will come to a halt. And so it doesn't violate the second law of thermodynamics to have the concentrations oscillate in time, as long as they go down to their final equilibrium value. It would violate if the free energy did that, but the concentrations can do it. But they can't just oscillate any old way. This type of oscillation and concentration does violate the second law of thermodynamics. If you go below the equilibrium value and then oscillate about it, that requires some kind of restoring force in a thermodynamic sense, and in a closed system that's forbidden. But you can have this kind of periodic behavior in the systems. So a very useful and simplistic way to model these problems is to think about the dynamics of the system. And a convenient way of understanding it is these phase plane plots. So here we have our chemical species U and V. So we've really reduced it to just a bare, grossly oversimplified. And so U and V are chemicals, the bromate and the bromine, for example, the rate-limiting steps. And then here's the dynamics of the system. You have the change in one of the species with time is a function of the chemicals. So in simple linear kinetics, you'd have the change in U in time is proportional to how much U is there and how much V is there, because if U and V collide, then there's some rate constant associated with it. So this can be quite complex and nonlinear when you have actually 90 intermediate steps. Then those taken all together become some nonlinear equation in one of the variables. And in this chemistry, that we say that